So we're pretty much done with processing in memory. Last week we completed it, and we've been talking about a lot of new paradigms. And this is another very interesting thing that could potentially change how we think about memories going into the future, and also systems going into the future. And if you remember, when I mentioned, when I talked about processing in memory, I said that some of these emerging memory technologies that are non-volatile, that do not need to move data when you actually need to operate on it, can be much more efficient, fundamentally much more efficient. And we're going to cover some of those technologies, even though I'm not going to spend a lot of time on how to do processing inside the emerging memory technologies. But you can imagine things like ambit, for example, that we discussed, analog operations that we tried to do in DRAM that brought us a lot of performance. You could actually do that inside these memories that are non-volatile without moving the data, without doing the row clone operations internally. Okay. So let's talk about what these are. Basically, we're going to talk about memories that are not charge-based. We've talked about a lot about DRAM, which is a charge-based memory. If you remember, the storage unit is really a charge storage unit. It's a capacitor. Whether or not there's charge determines whether or not you store 1 over here. We're later going to talk about flash, if we have time. That's a non-volatile memory technology that's not that's still charge-based, and here you actually store the charge inside this floating gate, and whether or not you have enough charge determines whether or not you have a 1 or 0 over here. Very similar to DRAM, but it's a very different mechanism, of course, as you can see. There's no capacitor here. It's really based on a floating gate that traps charge internally inside. So the problem with charge-based technologies is that it's difficult to place and control charge. And we've seen that in DRAM quite a bit, right? DRAM leaks very heavily. Whenever you access the memory, you destroy it, actually. It's a destructive read. That's why the sense amplifier needs to sense whatever you have over here and then restore it back. There's a restoration process that needs to happen to keep the data intact, either over time or because of an access. That's reasonably true over here also, actually, although there are some differences that we will discuss if we talk about flash memory. But basically, it's, these memory technologies actually are very much vulnerable to charge being affected by many things. Rowhammer is a very good example of charge being affected by activating neighboring word lines, for example. That happens in flash also, redisturb effects. It's going to happen in resistive memories also, but it's easier to do when you're charge-based. And also, basically, reliable sensing becomes difficult as charge storage unit size reduces. When we reduce the size of this capacitor and this floating gate, it becomes much more difficult to sense the charge. As a result, people have been looking at alternative technologies for a long time. And we're going to talk about some of those alternative technologies. But before we go into that, remember, just to give you the big picture, we've been talking about the memory problem, and we've been talking about 2 solution directions. One is designing new memory architectures. Whatever we discussed previously, memory-centric system design, better interfaces, better functions, better management of waste, efficient utilization, for example, for latencies. We don't want to waste latency, and we looked at the heterogeneity in latency quite a bit and tried to take advantage of that heterogeneity. Those are very good ideas. There are many key issues to tackle over there. These all apply to emerging memory technologies also. So keep that in mind. Whatever we discussed so far, at some level is applicable to emerging memory technology. Maybe not exact mechanisms, but some of the mechanisms are very much applicable. Like reliability at low cost. At least the key issues are still applicable to emerging memory technologies. We want to enable reliability at low cost so that we can get high capacity. We want to reduce energy as much as possible. This is going to be even a bigger issue in emerging memory technologies in some senses. Like activation, whenever you access memory, it's going to be very high power in some of these technologies that we will see, like phase change memory. Latency is going to be even a bigger issue in some of these technologies because fundamentally to access the device it will take longer. So we will see. Improving bandwidth will be important, especially write bandwidth will be an issue, especially in phase change memory. And reducing waste is always good, and we may or may not talk about a lot of these within the context of emerging memory technologies, but whatever we covered so far, keep in mind is applicable. And as I already said that enabling computation close to data is perhaps even better with emerging memory technologies. So everything we discussed so far applies to emerging memory technologies. Keep that in mind. Even though we gave examples from DRAM because we were able to, the big advantage with DRAM is it's already a very successful technology. it exists. Whatever improvements you make over there can go into products relatively easily compared to this, maybe, minus the mindset that people may have in the world. And also there's a big advantage that we really have existing chips in the field that we can measure, understand, model, and develop new techniques based on the understanding that we developed. And that's exactly what we discussed. Whereas in emerging memory technologies, you will see that that's really not the case. Actually, I'm going to show you examples where people actually show a lot of contradictory results in terms of the read latency, even something as fundamental as read latency of a technology, right? Because it's emerging, people don't even know exactly what the materials should be to construct a technology. As a result, things are very different. So it's not as easy to do research in emerging memory technologies. Hopefully it will be clear, but all of these things still apply over there. Okay, you saw the slide before actually, so I'm going to go through it quickly, and we covered some of these papers over here. Okay, so this is the second solution direction that we're going to examine. Basically, there are some emerging memory technologies that are more scalable than DRAM because they're more resistive. Because they're not based on charge storage, they're based on capturing resistance and encoding that resistance as bits, basically. We're going to talk about that. And they also happen to be non-volatile on top of that. I mean, you don't have to be resistive to be non-volatile. Flash is non-volatile, for example, but it's charge-based. But these technologies happen to be non-volatile as well, meaning that whenever you unplug the power, the data still stays over there. Right? Okay, one example is phase change memory. I'm going to talk a lot about this one because it's very interesting, and we know a lot more about this one than others. This may be the technology that's in Intel's 3D X point, although Intel still hasn't admitted it. That's okay, but we don't know, of course, right, for sure. But phase change memory is very interesting. This is one example of the technologies. Here you store data by changing the phase of some material. It could be chalcogenide glass, but it could be some other material. And the data is read by detecting this material's resistance. And this material exists in two states, amorphous and crystalline, and we're going to go into a little bit more detail, although not the nitty-gritty of exactly how this works at the device level. That's not the purpose of this course. So this is expected to scale to much smaller nanometers than where we are at DRAM today after so many years of investment, right? And it was actually prototyped at 20 nanometers. This is a beautiful paper from IBM Journal of Research and Development that describes the technology at that time. This is 2008. When we actually started looking at this, it was around 2007 or so. And this was one of the very nice papers at the time. It's still a very nice paper, so I'd recommend reading it if you're really interested in the device at the lower levels. But because it's resistive and it can scale to actually much smaller nanometers. And DRAM, as we discussed today, we're at about 17 nanometers. It's not clear if it will ever scale down to 9 nanometers or so. We'll see. And there's another advantage of these technologies. They expect to be denser than DRAM because they can store multiple bits per cell. Because they can chop off the resistance range into multiple intervals or multiple levels. And each level can encode a number of bits, basically. You can chop, for example, a resistance range into 4 levels, and you can encode 2 bits per cell if you have 4 levels. And we're going to see examples of that also. It's very hard to do that in DRAM. Okay, the problem is, this sounds very good, of course, right? There's always downside to any technology as well. There are many shortcomings to emerging technologies. And these shortcomings, some of them are common between technologies, some of them are different, technology specific. The key question that we're going to ask is, can we somehow enable these technologies to replace, augment, or maybe even surpass DRAM based on system level and architectural level mechanisms? Okay, we're going to cover some of these papers. Okay, so basically this is the fundamental difference between the technologies that we've discussed so far, DRAM at least, and we're going to discuss today. So DRAM and flash, they're charge-based memories. You basically write data by capturing some charge into a charge storage unit, and you read data by detecting the voltage. In resistive memories, there are multiple, you basically write data by pulsing current into a device, and then you read data by detecting the resistance. And there are multiple ways of doing it. I'm not going to go into the read devices. But if you're interested, you can definitely, I would definitely recommend this IBM Journal of Research and Development paper. Okay, so there are some promising technologies. This is not a comprehensive list. This is a list that's interesting to me especially, but there are other technologies over here that could be added. I may mention some of them. But phase change memory is something that we're going to spend a lot of time on. Basically, this is a technology where you inject current to change the phase of some material. And material phase encodes data, and resistance is determined by the phase of that material. And we're going to detect the resistance. STT-MRAM, this is a magnetic technology, spin transfer torque, magnetic memory. You inject current to change the polarity of a magnet compared to a reference magnet, and the resistance is determined by the polarity of that magnet that you can control. Memristors, RRAM, ReRAM, these actually, I categorize them together. There are slight differences between them, but that's okay. We're not going to into a lot of detail over here because I know these the most. Even though I know these the most, I always figure out that I don't know enough about these new technologies, so that's always good to keep in mind. But definitely I know these the least. But basically the key thing over here is you inject current to change some atomic structure, and resistance is determined by atom distance, at least in some of these, some subset of these memristor-based technologies. And there's also other technologies like conductive bridging RAM, ferroelectric RAM, other things that may be interesting. Some of them are already employed actually. They're not necessarily emerging technologies, but they're resistive still. So let's go into phase change memory, a little bit more detail as to what the technology is and what can potentially bring and what are its downsides. Basically, we're talking about phase change material. Chalcogenide glass is one example, but there are many materials. I'm going to show you a table in a few slides where people have looked at many different materials. But this material exists in two states. One is called amorphous. It's a high electrical resistivity state, and the other is called crystalline. This is low electrical resistivity state. So you can distinguish between these two states. It turns out this material in the amorphous states has also low optical reflexivity, and in the crystalline state has high optical reflexivity, meaning you can actually detect the state of the material by shining light on it, right? By optical reading. And we know how to do this really well. We built rewritable CD-ROMs, and they actually use phase change material in them. So this technology is actually already widely employed. Well, I don't know how rewritable CDs are actually employed today, but okay. It was employed in the past and was successful in the past. Of course, the problem with this sort of reading and writing mechanism using optics, at least into this technology, is it's relatively slow. So you don't want your rewritable CD to be your main memory. It's possible. You could actually try to do that, right? There's nothing that prevents you from doing that, but it's just too slow for our purposes in designing a fast computer. So the nice thing that has happened in the past years is there's been a lot of research on how to... What's happening here? Maybe some new technology is shaking the ground. Okay. We don't normally have earthquakes here, right? Okay. But something is certainly happening. Okay. Basically, what has happened in relatively recent years is people invested a lot into developing read devices, basically devices that can detect the resistance of what is stored in the storage device. There's a lot of work in this area. IBM has done a lot of work especially. You can find some of that work in that paper that I mentioned, but there's a lot of work since then as well. And people were able to develop very reliable and very fast read devices. You can think of them as sense amplifiers, kind of, but they detect the resistance so that they can detect whether you're in the amorphous or crystalline state, or what resistance range you are in. And that's fascinating by itself, but that's a very long, low-level lecture, which we're not going to get into. You guys are okay, right? Okay, we should continue, I think. So basically that's why this has become really interesting recently. Even though this technology was very well known since the late 1950s, early 1960s, and it's very well employed in rewritable CDs, the read devices were not fast enough for main memory purposes, but these devices became fast enough for main memory purposes now. As a result now, we have prototypes of phase change memory that can be switched between states reliably and quickly. And people usually draw things like this. You essentially have this chalcogenide material, and these are the axes. That's your bit line over here. This is the axis word line, and there's basically you can heat this material, and we're going to see how you read and write to it. Why you need that heater. Basically, in order to be able to change the state, you need to heat. You need to inject a lot of current. So how does it work? In order to write to this, you need to change the phase of the material by injecting current. And of course, set and reset are different. And this is an example over here. If you're really interested, again, I would recommend that IBM paper. Basically, in order to set, you need to inject some sustained current to heat the cell above some crystallization temperature. So it looks like this, basically. You heat the cell for a long time. And in order to reset the cell, you basically heat the cell very quickly above a melting temperature and quench it also very quickly. So it looks like this. That way you can set or reset. Basically set the resistance to some level. That's what it means, set and reset, right? So different levels. And reading happens by detecting phase via material resistance, and that's the read device that I mentioned, whether you're in the amorphous or crystalline state. And people actually manufacture these. This is pictures from IBM, where they show that this is the set state, it's low resistance, and it looks like this. You can observe the material, and this is the reset state, that's high resistance, and it looks like this. That they call kind of like the mushroom cloud, something like that. Yeah. Okay. So you can read a lot more about the device level also. So what is the opportunity that is enabled by a technology like this? First of all, it scales better than DRAM and flash. It requires current pulses, which scale linearly with feature size to change the set or reset, basically. And as I said, it's expected to scale to 9 nanometers. This was predicted by ITRS. At the same time, they predicted that DRAM is going to be not so easy to scale below 35 nanometers, as we've discussed earlier. They were predicting this is going to scale to 9 nanometers. And today, the predictions are actually much lower. People are saying, oh, this could scale to 4 nanometers or so. There have been some very small-scale prototypes already around that nanometers. And a long time ago, it was prototyped at 20 nanometers. So basically, it can be more cost-effective than DRAM and flash if scaling continues like this, and DRAM and flash scaling becomes more expensive. So scaling enables you higher cost, lower cost, and also higher capacity as well, right? There's another benefit from phase change memory in terms of density. This can be denser than DRAM, not because it can also scale better, but also because you can store multiple bits per cell because you have a very large resistance range. And people have prototyped this memory as early as in 2008 as 2 bits per cell. And this slide is old, so there are already prototypes with 4 bits per cell actually by chopping up the resistance range. So it's good. It's non-volatile. You can retain data for a long time, as you can see, at 85 degrees Celsius. So here you should be thinking about the worst case. So all of the worst case, common case techniques that we discussed could be applicable to all of these technologies also. And there's no refresh that's needed because of non-volatility. As a result, you get idle power reduction, significant idle power reduction. So it sounds very good, right? Well, it's not going to be as good, actually. This is not necessarily completely true because it turns out there are other mechanisms that cause reliability issues in this memory. The resistance range, for example, shifts because you lose some resistance over time. As a result, you need to replenish the resistance that you have. So it's very much like refresh. But the time scales at which you lose resistance is much larger than the time scales at which you lose charge. So your refresh is not going to be as frequent as you have in DRAM. Okay, but this sounds good theoretically, right? No refresh needed. And refresh is a key scaling limiter of DRAM. So if we actually get rid of this, this technology sounds very, very appealing. That's why people have been examining it for a while. Okay, so let's take a look at this multi-level cell phase change memory. So if you think about phase change memory cell, you can basically have basically a resistance range, and you can chop up that resistance range into 2 and have a read reference resistance, right? This is your resistance, that's a reference, and if the cell is below that resistance value, you encode as 1, otherwise you encode as 0. So it's obvious. In DRAM, you also have something like this. But in multi-level cell PCM, you can basically have more than 1 bit per cell, and this increases density significantly. The problem is this also has drawbacks. You get higher latency and energy than single level cell PCM, but this gives you higher capacity. It looks like this basically. The same resistance range that I just showed you earlier is now divided into 4, which is good for capacity, but how do you read it? Usually when you read something like this, you first try to distinguish the most significant bit. For example, you apply a read reference voltage over here, and you figure out whether you're here or here. And then once you figure it out, you apply the read reference voltage either here or here. And then you figure out which of these 4 states you're in. So you could actually do a hierarchical method like that. Does that make sense? Okay. So that's why it takes longer to read. That's one method that I described. There are multiple methods that people have developed over time. And when we cover flash memory, we will see particular methods also. So basically, if you have something like this, that's good. But the downside is now you need more precise sensing and modification of the cell content such that they fall into these buckets. And the margin between those buckets is not as large as the margin that you have over here, right? The same cell resistance is divided into 4 over here. And as a result, you get higher latency and energy. So read latency is higher and write latency is higher because you need to be, you cannot just program things to just over here or over here. You need to chop them into finer grained pieces. Okay. Okay, so any questions so far? That's some basics on multi-level cell. Multi-level cell exists in flash also, so we're going to talk about that. Yes?
Do the cells age?
Do the cells age?
Like with lots of age and red?
Yes, we're going to talk about that, yes. They do age and they wear out. As a result, at some point, some of them die, meaning that you're not able to read or read from them or write to them reliably. So phase change memory is a technology that has this endurance problem. That's what you asked, right? But not all technologies have the endurance problem. We're going to look at STT-MRAM that doesn't have that endurance problem. Yeah. Okay. Okay, we didn't cover the downsides fully yet. Any other questions? That's a very good, yes.
Could you go back one slide?
This one?
Does the way that you encode the different states change anything at all?
Yeah, it's good. There's actually a lot of work related to that. The way you encode determines how you can correct errors, for example. So a lot of these memories require error correction, and your encoding may affect that. Because some errors are more likely than others, actually. I mean, clearly, the probability of a cell jumping from this resistance value to this resistance value is much lower. So if you encode your states nicely, such that only 1 bit changes between these two, actually helps. So this is probably not a good encoding, actually. Yeah, you need some sort of gray codes, for example, that helps. But people have looked at other codes as well. That's a very good question also. Okay. Okay, so now let's take a look at this, this technology a little bit more from an architectural perspective. So as I said, we started looking at this around 2007 while I was at Microsoft Research, and there was not much work at the time. And we thought phase change memory is very, very interesting. We'll see if we were right after Intel decides to disclose their 3D X-point. By the way, I talk about 3D X-point, but flash forward to right now. 3D X-point is an emerging memory technology that Intel designed with Micron. And they actually put out the Optane SSDs. These are SSDs that you can buy and use. And they promised to put out the memory version of 3D X-point sometime next year, I believe. So if that happens, then it's going to be very similar to what I'm going to describe over here. We don't know, of course, the characteristics of what the 3D X-point will be when it's put out, but that's exactly the exploration that we had done with this paper that I'm going to describe. So it'll be very interesting, actually, if that could be used as a main memory replacement. Okay, so basically what we did at the time, we didn't have those DIMMs. We still don't have those DIMMs. We surveyed prototypes of phase change memory that were published in multiple different low-level, device-level conferences. And we tried to derive reasonable parameters for phase change memory for a feature size of 90 nanometers. So 90 nanometers is very high, but that's okay. We want to explore the latency, bandwidth, energy characteristics. And this is one of the tables that we derived. As you can see, on this table, we have these parameters in the rows, different types of parameters. What is the material? What is the year? What is the process technology? What's the array size, cell size, read time, read current, read voltage? So you can actually keep going over here. And these are the papers that we found in the literature that actually describe their prototypes. Some of them are from industry, some of them are from academia. And the takeaway is, if you look at these double stars, it says this information is not available in the publication cited. So the takeaway is you don't know most of what you're dealing with at that time, especially. Most of the things are not given. There are a bunch of papers where you actually have some of them. Actually, this one is, for example, a lot of our results were based on this one, but not all of them. And also, the second takeaway over here is because people use different materials, for example, over here, and also they use different processes, and they also have some different ways of interpreting and different prototypes, you get very varying numbers over here. For example, the set time over here for this work is about 80 nanoseconds. And in this work, it's about 400 nanoseconds. And that's a huge difference, right? That's 5x difference. And if you look over here, this is the write endurance. How many writes do you need to do, can you do to the cell before the cell dies? Meaning cell wears out, you cannot do anything to the cell. This work reports 10 to the 4 writes, which is very low. And this work reports 10 to the 9 writes. That's 5 orders of magnitude difference. So you see what you're dealing with. This technology is not out there, so you need to actually figure out what to do with it. And it's very important to do this sort of research because that's how you enable a technology going forward. If you say, oh, I'll wait until this technology is out, that's a bit late because that technology may never be out because you didn't do the research. Right? So it's a chicken and the egg problem, actually. But when you're doing the research, it may be difficult. Yes?
How often are DRAMs written to usually? So, memory intensive program.
Yeah, so you can actually, I'll give you some results as to what you would get if this is the number, but it's much, much, much more than 10 to the 4. Because 10 to the 4 is really 10, is it 10,000? It's 10,000 actually, yeah. So you can compute, right? If let's assume a write takes 100 nanoseconds, that's actually very long. How many writes do you do, if you have a day, how many writes can you potentially do if you keep writing to memory? It's going to be much more than 10 to the 4, right? It's actually a lot. So you actually, write endurance is a huge problem with these memories. By the way, this 10 to the 4 is not terrible. If you look at some of the flash memories that we have today, that's actually much lower than 10 to the 4. That's why we're going to cover flash memory later on. But the difference between flash memory is used for storage, right? And there's a lot of buffering, write buffering that happens until you write to your storage device. But if you use it as main memory, then you have a big problem with this write endurance. If all of the writes directly go to your main memory after your caches, yeah. Okay, so some of the initial results are not going to be that promising because of that. And we're going to try to tackle that problem. Okay, so hopefully this is interesting. But I just want to make the point that you don't know enough about the technology, but this research is critically important to do if you want to enable the technology going into the future. Okay, so let's take a look at where some of these parameters stand in terms of the current hierarchies that we have. So I like this picture. This basically shows the typical access latency of different technologies as they're employed in terms of processor cycles for a 4 gigahertz processor in this case. So if you look at SRAM, that's very fast. Embedded DRAM, it's very fast. DRAM is very fast. There's flash. There's a big gap between DRAM and flash over here. This is 2 to the 17 processor cycles, which is a lot. And hard drive, there's a big gap between flash and hard drive also. That's why flash has been very successful by getting over here, right? It bridged the gap between DRAM and hard drive, which used to be huge. Now, where does PCM, phase change memory, sit? It sits very close to DRAM, actually. That's why it's very interesting. The key question that we asked was, can we actually replace DRAM with this technology with some architectural improvements? Okay. So, but now let's go to the downsides a little bit. The properties, latency is actually very good compared to flash, but not so good compared to DRAM. So according to the parameters that we saw, it was 4x compared to DRAM, but much better than flash. Write latency is actually more than an order of magnitude larger than DRAM, at least according to our assumptions. Some other people assumed more aggressive write latencies for phase change memory, like 4x of DRAM, but we'll see. We don't know exactly how it will pan out. But writes are a problem because of the reason that we said, right? You need to actually melt the material, and that takes time, and that also takes energy. As a result, your write bandwidth is also relatively limited compared to DRAM. But your write bandwidth is reasonably on par with flash at the time. Okay, there are more reds over here. As you can see, the energy is much worse than DRAM. The read energy is about 2x of DRAM. And write energy, because you need to melt the material, it's about 40x of DRAM. So this sounds bad now. Maybe you don't want to write a lot to this memory, you're thinking, and you're right if you're thinking that way. If you're reading from this memory, that's not bad maybe, but if you're writing to this memory, that's not very good. But the dynamic energy is actually on par with flash, that's good. Endurance, this is a big problem actually that doesn't exist really in DRAM. So you have this endurance problem because you need to write to this memory, and they induce phase change at very high degrees. 650 degrees Celsius is one example. People are trying to reduce it, of course. You don't want that high temperatures, but you need high temperatures to melt this material. That's why people have looked at a lot of materials as well in this technology. And if you actually operate at those high temperatures, your contacts, electrical contacts, degrade because of thermal expansion and contraction. And that's one of the major causes of this wear out in this technology, if you do it enough times. So in our work, we're going to assume that you can do 10 to the 8 writes per cell. Now, as you saw that some people reported 10 to the 4 writes per cell. That would be terrible for main memory. I think even with 10 to the 8 writes per cell, it's not going to be very nice in the results that we will see. Now, this is actually better than flash. And actually, flash is getting worse. When we talk about flash, you will see that there are some flash technologies where you can do only 100 writes into a cell. It's called triple level flash, basically. It's very, very high density flash that could be used for cold storage, for example. Maybe you write once and you don't read much after that. Very high density, but reliability, endurance is very low because you chop up the voltage range in flash memory into essentially 8 different levels. And as a result, you have an endurance problem. Okay, but this is better than flash, which is good, but it's not as good as DRAM. So DRAM technically is supposed to have an endurance of infinity. Now, if it's not clear if we can measure that. But DRAM advertises itself as a technology that doesn't have an endurance problem, which is subject to debate because it's not clear if people have used it enough and report enough data in the field. But certainly DRAM is not that easy to wear out. Okay, that's why this 10 to the minus 8. Maybe this is too aggressive over here, but it's not that far from the approximate reality. Okay, so these are all downsides, right? But cell size is actually not bad. So basically, you can have a good cell size. Your density is higher than DRAM and much higher than NAND, and hopefully this will scale with feature size. That's the goal over here. Okay, so let me summarize over here. Basically, what are the pros over DRAM? So we're not going to compare to flash right now. Actually, if you want to compare to flash, you can buy the Optane SSD, at least in one technology. And you could actually see the difference for yourself. I don't know what it is. It'd be good to see some reports with that. But it's not a mature technology. Of course, flash is very mature. Optane SSD is not very mature right now, right? That's the first incarnation. It's always good to keep that in mind when you're doing comparisons. So let's compare to DRAM. If you compare a phase change memory to DRAM, as I said, you get better technology scaling. So hopefully better capacity and a better cost point at some point in time. That's very good because DRAM is suffering from technology scaling problems. You get non-volatility, which means that you can have persistence in your main memory bus, right? Meaning that you can manipulate persistent data on your main memory. And we will talk about that toward the end of this particular lecture. How can you enable that? What kind of benefits can it buy you? Maybe you can bypass all of the file system if your main memory actually can operate on persistent data and change your programming model such that you directly operate on your own persistent data without going through files, right? Now that could be revolutionary actually because file management, yes, people do it, but it's a lot of overhead in the system. We will see that. So there's an opportunity over there. And also you get low idle power, you have no refresh. In addition to being more technology scalable, because of that, you also get power benefits clearly. Now the cons, you get higher latencies. Unfortunately, read latencies are high, write latencies are even higher. You get higher active energy whenever you access. Read accesses are higher energy, write accesses are especially higher energy. You get lower endurance, unfortunately. A cell dies after some number of writes. We're going to assume 10 to the 8. And you have some reliability issues which we're going to ignore for the purpose of this evaluation, because this is true with any memory technology, as I said earlier. It's certainly true with emerging memory technologies, but it's a lot harder to examine with emerging memory technologies because they don't really exist, so you cannot measure them really well. You can guess, model, do circuit level evaluations, but as I said very earlier, even in DRAM, we do not know how to exactly model these issues. As a result, we're running into problems like row hammer, for example. So if you cannot do it in existing technologies, you can imagine that it's going to be orders of magnitude more difficult to do it with an emerging technology where you don't really have the devices yet. Right? So that's why we're going to ignore the reliability issues, but this doesn't mean that they don't exist. Actually, some of the reliability issues can threaten the existence of some of these technologies. Resistance drift is one example. As I mentioned, charge leaks, resistance drifts. You can think of it as resistance leakage also. There are also read disturb issues, similar to row hammer. Over here, there are write disturb issues. Whenever you write, you actually destroy adjacent cells. That could happen. So, okay, but we're not going to get into that because DRAM also has these reliability issues, as you know. Okay, so basically the key question is, how do we actually enable phase change memory as a DRAM replacement or an helper, or augmenting DRAM somehow? Initially, we're going to be aggressive and look at trying to replace DRAM. To be able to do that, clearly, we have to do something about these reds. And we need to find the right way to place phase change memory in the system. So this was a picture that we drew about 10 years ago, 11 years ago now, I think. We were asking the question, how should phase change memory-based main memory be organized? And that was the system at the time. And we thought, take this with a grain of salt, it's a cartoon. We thought you could actually go into a hybrid memory, and that's an initial step. Eventually, if the technology scaling is really well with this sort of technology, maybe you'll completely replace DRAM with this new technology, phase change memory, for example. And we're going to examine this solution. I think this is quite aggressive, even today. This other solution we're going to get back to. We're going to talk about some papers that also looked at hybrid phase change memory and DRAM. Here, the key question is, how do you partition and migrate data between phase change memory and DRAM? And we're going to talk a lot about that. And how do you actually design the DRAM in this case? Is to cache the phase change memory. If you cache the phase change memory, how do you design that huge cache? So we're going to look at it from that perspective. And also, again, this is a cartoonish, so it doesn't have to hang off the same memory bus, right? It could be two memory controllers controlling, one controlling DRAM and the other controlling phase change memory. So it's heterogeneous hybrid memory in this case. So this is the more aggressive one. This is the one that really excited us at that time. I think it's still very exciting, but we'll see. So this is pure PCM-based main memory. If you have this, and if you have all the reds that we've discussed, then how do you design the entire hierarchy and maybe the cores to overcome the shortcomings that we have? And I think there's still a lot to be done in this area, but let's see. I'm not fully convinced that this is the only option. I think we should probably explore both of the options going forward. But phase change memory may be a difficult technology to deal with because of its characteristics. Okay, so basically what we did in this work was we surveyed the prototypes that were published that I gave you the huge table for. And we derived some average phase change memory parameters for a feature size of 90 nanometers. And these are the parameters that we're going to deal with. We're going to simulate what happens if we actually take out DRAM from the system and replace it with phase change memory with these parameters. We're going to ignore density in this evaluation. Basically, we're going to assume same capacity DRAM and same capacity PCM. This actually puts the technology, phase change memory, at a disadvantage, I think, because assuming that it's more scalable, it's going to be more dense. So for a given amount of DRAM in the system, you should be able to put more phase change memory into the system. But we want to be pessimistic initially and see what happens assuming that you directly replace DRAM with PCM without increasing the density. And clearly we're going to lose performance because of this, right? Your latencies are going to increase because latencies are much higher than DRAM. Energy is going to increase and endurance will be a problem. So let's take a look at what happens to applications if you actually replace DRAM with phase change memory in a 4-core, 4 megabyte L2 based system. And we run these applications. These are more or less scientific applications at the time that we got our hands on, and they were interesting. I showed you some of these before, but for example, this does earthquake simulation. This does some image modeling, shallow water image modeling. They're really interesting applications over here. This does conjugate gradient computation, for example. FFT is obvious, hopefully. Hopefully many of you have done FFT. Okay, good. But basically, these may be some intensive applications, but they're not extremely intensive also. So we're simulating what happens to delay, meaning performance in this case. What is the performance of the application? Actually, execution time of the application. And the energy consumed in the memory for the application if we actually replace DRAM with phase change memory. And organize phase change memory the same way as DRAM. Same row buffers, same banks, same peripherals. Nothing changes. You can imagine this as taking a single DRAM cell out, replacing it with phase change memory, and accounting for the characteristics in the simulation. So the results are not good. Basically, if you do that, the performance loss is about 60%. Averaged across these applications, but some applications, as you can see, lose a lot more. The performance loss over here is 1.2x, right? 120%. Basically, you slow down by more than 2x if you actually reword this. That doesn't sound good. The energy increases by 120%. Basically, our energy consumption is 2.2x. That doesn't sound good also, although take this with a grain of salt. Energy is always harder to evaluate. And it turns out your memory dies after 500 hours because of the endurance problem. Right? Basically, these applications write to memory reasonably often, and you can only do 10 to the 8 writes into memory. As a result, they basically eat your memory away as they keep writing. And that doesn't sound good also, right? You don't want a memory that gets destroyed after 500 hours. This is a real problem with flash, of course, but this is an even bigger problem if you actually put a memory like this on the memory bus. And actually, you can see that the years, this is the years until which the memory lasts. So it lasts less than 0.18 years maximum for all these applications, right? And we're not even running multiple applications together over here. Okay, that sounds bad. You don't want this sort of technology, if you will. But what can we do about it? So we actually wanted to architect the memory such that we can overcome this. This is non-architected. This is a naive replacement of DRAM with PCM. So if you have this sort of memory, as I said, this is going to sound funny maybe, but you don't want to write to it. And you don't want to actually also read from it either. So you basically want to protect this memory. It gives you very high capacity, and you want to access it very little, if it's possible. That's the idea. At least, that was what we tried to do. So basically, we didn't want to change the system very significantly because we didn't want to go into a hybrid memory, as I said. We wanted to just look at phase change memory. So this is what we did. We actually changed the organization of phase change memory chips. So the first idea, if you look at DRAM, DRAM has a row buffer, which is sense amplifiers, and the size of that row buffer is large. And it has to be large because whenever you activate an entire row, you destroy the entire row. So you need to sense the entire row, and you have to have a single row-wide row buffer or sense amplifiers. That's not necessarily true in PCM because phase change memory, whenever you activate a row, you read the data, but it's not a destructive read. The data stays there, which means that these sense amplifiers don't need to sense everything in the row, right? They just need to sense whatever you're trying to read. Make sense? So you can make this really small. It doesn't need to be row-wide. There's no reason. In DRAM, the technology dictates that it has to be row-wide if you're doing a row-wide read, activate. So what you can do now, you can have a narrow sense amplifier, but you can have many of them, like a buffer over here, and you can manage them as a cache. And that's exactly what we did. We use multiple narrow row buffers in the PCM chip. This reduces array reads and writes because now you can actually manage this nicely, hopefully, as a cache internally in every bank. You could potentially do it at the subarray level also, but we didn't do it in this work. Okay, so that's one thing. This way you can, for example, buffer the writes over here before writing them into the phase change memory, buffer the reads over here, such that you can actually get better caching. This reduces, this gives you better endurance. It reduces the writes into the array. It reduces the array latency because reading from these latches, these are SRAM. Remember, this is SRAM, this is SRAM. reading from these latches is much faster than reading from the data array, and it's much more energy efficient than reading from the data array also. Basically, as I said, we don't want to write to the data array yet. We don't want to read from the data array, so we're going to add the caching structure. And we were limited in what we did because we wanted to be cost equivalent to DRAM. We didn't want to change the amount of sense amplifiers over here, so let's assume that this was 8 kilobytes, so the total cost of this would be 8 kilobytes also. And you can read the paper for more detail. So we were not too aggressive. I think you can be more aggressive and do even better. The second idea is, actually this was employed in many phase change memory prototypes afterwards, is basically whenever you write into the data array, you don't write at a very high granularity. You basically write back only the words that have changed, or only the bits that have changed actually. We didn't look at bits over here, but we look at words, for example. If you actually do that, you reduce unnecessary wear. Basically, you don't write to all of the cells in the row, you write to some of the cells in the row. That's the idea over here. And that's good. Actually, Samsung had a bunch of phase change memory chip prototypes where they did it internally in the chip. What they did was, every write was a read modify write. What they did was basically, they read whatever granularity they were doing the write in, let's say word granularity. They read the word. They compared that word to what was supposed to be written at that time, and at the bit level they figured out what are the differences, and they only changed the bits that were different from the memory array. That way you reduce the wear. And internally they had this mechanism inside the chip, phase change memory chip, which I think is good because now you can do comparisons also internally inside the chip, right? If you're not using it for some other purpose. Okay, let's assume you have these ideas. What do they buy you? Now take these results with a grain of salt. Your performance improves with these ideas because you do much better caching over here. As a result, your performance degradation, because you replaced DRAM with phase change memory, goes down to 20%. Which doesn't sound too bad, but the problem is there are a bunch of applications that get affected a lot. Energy, take this with a huge grain of salt. Energy becomes on par with DRAM. But energy models are hard to get. I think this is still not necessarily correct, but clearly your energy becomes much better than what it was before. Before it was 2.2x, if you remember. Now it's closer to 1x. And your average lifetime improves from 500 hours, now you're at 5.6 years. But that's average. So it sounds better, but it still doesn't sound very good. Well, you could argue that if you actually scale, that improves energy, that improves endurance, that definitely improves density, hopefully, but that's not clear also. Well, at least endurance and energy are not fully clear, but latency doesn't improve, for example. Okay, so there are many caveats here. One is worst case lifetime is much shorter. If you look over here, for some applications, some very memory intensive, write intensive applications, they still destroy your memory very quickly. This is about 1 year, right? If you look over here, it's actually less than 1 year. Even if you do this writes at a smaller granularity than the row granularity. Okay, so no guarantees. So this becomes an attack vector also, right? Some application can attack your memory right now, and it can destroy the memory for other applications or the system. And there's some work in this that I'm not going to get into. The second is intensive applications see much larger performance and energy hits. So if you really care about the performance of an application and they're memory intensive, you're going to lose more performance. This doesn't sound good because those are the applications that you really want memory to perform well in. As a result, maybe that's not a good solution, at least with this solution. And maybe we used optimistic phase change memory parameters, and that's still not clear to me yet. And that's not going to be very clear even after phase change memory chips are out in the field, because those will not be the mature phase change memory chips initially. So we'll see, I think. This remains to be seen. So this is a pessimistic paper from that perspective. But it does a very fair comparison between DRAM and phase change memory with the same capacity comparison. But I think the takeaway is it's going to be very difficult to completely replace DRAM with a technology that looks like this. At least by trying to completely replace DRAM. Okay. Maybe you keep some DRAM in the system and some phase change memory. We're going to talk about that solution a little bit. And this is the paper. I don't know if we've assigned this in a homework, but we might assign it. And you might be interested in it. And actually, this is an extended version of the paper that is written with some other folks who were actually doing concurrent research with us at the same time. There was a session at ISCA International Symposium on Cache Architecture. This is different from caches. Although, as you see, we did some caching internally, right, in the chip. So we're still eligible for the conference. Basically, there was a session in this conference. The first session actually was dedicated to emerging memory technologies, and there were 4 papers, and this was the first paper that was presented. I'm going to talk about the second paper in a little bit also. Okay. Any questions? Does this sound good? Interesting? Exciting? Well, I think it's pretty exciting. Okay, let me talk a little bit more, and then we'll take a break in a little bit. So this is phase change memory. I think it's very interesting, but it's always good to explore many technologies, and I'm not taking any sides with any of the technologies. I think some of them, all of them have advantages and disadvantages. We later examined STT-MRAM. I think this is very, very interesting also, and I'll give you the upsides and downsides. Why is it very interesting will become very clear in the next slide, actually. But let me tell you about the technology a little bit. Basically, this is another emerging technology. What you have is something that's called a magnetic tunnel junction device. If you really want to learn about it, you can search for it and figure out papers. I'd be happy to send you some. And this paper that we wrote references some of them also. Basically, the idea is very simple. You have 2 magnets. One is a reference magnet that always has a magnetic field in one direction, fixed magnetic orientation, let's say. And there's a barrier, and there's another magnet after that that could be parallel or anti-parallel to this reference layer, depending on its magnetic orientation. And you can change the magnetic orientation of this free layer. And which way it's oriented determines the logical state of the device. So in this case, you see there's low resistance, and in this case there's high resistance, and as a result, you get a logical 0 or logical 1. That's the idea. And you can detect this resistance with, again, read devices that are customized for this technology. Sounds good, right? It's actually very nice, I think. It's conceptually very intuitive. Basically, in order to write, you need to push large current through this magnetic tunnel junction device to change the orientation of the free layer. Of course, you need to inject enough current to change that orientation. And when you actually read, you sense the current flow. And there's a lot more detail in this paper with some references. Let's take a look at pros and cons of this technology. Pros are very similar to phase change memory. Nothing is actually different. You get better technology scaling, better capacity and cost. You have non-volatility. As a result, you can exploit persistence perhaps, and you have low idle power, no refresh penalties. But the benefit actually comes from the cons over here. You get higher write latencies because actually changing the orientation of the free layer takes some amount of time, especially if your magnetic tunnel junction device is very large, and it needs to be large actually for reliable operation today. But you don't have a read problem. Read devices are actually here relatively fast, so reads are on par with DRAM. Now that's actually very good, because read latencies are much harder to hide than write latencies. Similarly, read energy is on par with DRAM, but write energy is much higher than DRAM. Unfortunately, even though this technology is very scalable, today, to make this very reliable, or reliable enough, you need to make the magnetic tunnel junction device huge. Huge, meaning that it's much, much larger than a DRAM cell today. You can think of this as the size of a magnetic tunnel junction, the size of a single STT-MRAM cell needs to be similar to the size of a last level cache cell, which is more than 40 to 60 times than DRAM, a DRAM cell size. So that doesn't sound good as a DRAM replacement at this point, perhaps. But if technology scaling actually is in favor of this, then at some point this could scale to be much better than DRAM, right? That's why it's good to examine this as a potential DRAM replacement. So because of what I also said just now, people are actually considering using STT-MRAM as a replacement for last level caches. Can we actually get rid of the last level cache that's implemented in SRAM today and replace it with something like STT-MRAM? And we get hopefully good benefits, plus, well, hopefully good benefits over here, plus non-volatility, right? If you have a non-volatile cache, now we can manipulate data persistently on the chip. You can actually store things that could survive forever while your chip is powered off, right? So this could have many, many benefits clearly. Downsides also, of course, right? Persistence always also comes, if you have some data that's stored over there, now if someone else can read it as well, right? So there could be concerns in terms of information leakage. Whereas whenever you power off something, you erase the data, or you think you erase the data. And as a result, you may have less leakage. So those are issues that I don't go into over here, of course, because that depends on the usage model of the technology itself. So this is the main reason why it's difficult, I believe, to replace DRAM with STT-MRAM today, poor density. But this is a memory technology. You could use it even in the register files, right, if you really want to. But let's not go into that right now. Okay, so reliability, as I mentioned, I'm not going to talk about reliability, but this technology has similar reliability issues like any technology. So this technology is also interesting because it gives you another level of freedom, which is you can actually trade off non-volatility of this technology for lower write latency and energy. So you can actually make write latency and energy almost on par with DRAM by reducing the size of the magnetic tunnel junction device. As a result, you unfortunately give up non-volatility and this persistence and some idle power. But now you become very close to DRAM in terms of both read and write energies. So that becomes very interesting. And also your size reduces. So in terms of density, you become slightly closer to DRAM. And this freedom has been explored, and I think there's more to explore over here. So perhaps, for example, you have memory that's heterogeneous, right? Some part of it is non-volatile, some part of it is volatile, and it's consisting of STT-MRAM technology. But we're not going to go into that right now. So let's take a look at what, we're going to do exactly the same study. Replace DRAM with STT-MRAM with these characteristics. And we're going to do some architecting, meaning that you need to deal with write latency and write energy somehow. And I'm not going to go into the details of the techniques, but they're similar to what I've just discussed for phase change memory, but there are a few more techniques that are in the paper. You can read about them. But if you do all of that, the results look actually very promising. Again, we're assuming the same capacity DRAM, same capacity STT-MRAM. In this case, STT-MRAM, in terms of cost, if you want to get the same capacity per cost, we're not there yet. But hopefully scaling will bring us at some point in the future. So the performance loss with some other applications, it turns out it's about 6% compared to DRAM. So you lose some performance because our writes are much longer right now compared to DRAM. It's about 10x longer. But it's not that bad. It's within 10% of DRAM. So this, you could imagine ways of overcoming this somehow, right? The energy benefit, take this with a grain of salt again. Energy modeling is not easy in general, but it's about 60%. It's certainly much better than what I just presented earlier to you, because you get rid of a lot of refresh and idle energy, and read energy is not a problem over here. Write energy is the only problem that you have compared to DRAM. So you save a lot and you lose on the write. So this looks very promising, and I think going forward this will become even more promising. But we're not there yet, because it'll probably take some number of years until we figure out how to design STT-MRAM cells that are very, very dense and very, very small and very, very reliable. But keep this in mind. And this could replace, as I said, on-chip caches or parts of on-chip caches earlier than this technology could replace DRAM, potentially. But we'll see. Okay, so if you're interested, you can take a look at this paper. Any questions? Well, we covered STT-MRAM also. So, as I said, it's not clear if any technology can completely replace DRAM. DRAM turns out to be very, very strong, as you can see. So maybe a more viable solution, at least in the short term, is doing something like this. And you've already seen this picture earlier in the lectures. Hybrid memory systems. You have some amount of DRAM in the system. It has some good characteristics and some bad characteristics. And you have a huge amount of, let's say, phase change memory or technology X in the system. It has some very good characteristics, but some very bad characteristics also. And they're complementary to DRAM. And you design the hardware and the software to manage data allocation and movement to achieve the good characteristics as much as possible while avoiding the bad characteristics as much as possible. So that's the notion of hybrid memory systems. And it was initially, now you can actually expand this. It doesn't have to be DRAM and phase change memory. It could be any technology, and there could be more heterogeneity over here as well. The downside is now you need to manage this heterogeneity somehow, right? How do you manage this heterogeneity? So a big challenge and opportunity going into the future is somehow providing the best of multiple metrics with multiple memory technologies. I think a big challenge is also getting rid of DRAM as much as possible in the system. I didn't say that over here, but that's kind of implied. So that brings us to more heterogeneous memory systems. And I think heterogeneity requires some configurability, and certainly programmability is needed to take advantage of this, and for the many other reasons that we've discussed earlier. So there are a bunch of issues with hybrid memory systems, but maybe we should take a break, because it's a good point to actually take a break for about 12 minutes or so. Okay, let's be back around 1:30 or so. Okay, let's continue. So we've covered replacing DRAM with an emerging technology. Now we're going to move more into hybrid or heterogeneous memories. And this opens up a lot of other complexities. So there are many issues in hybrid memory system design. Again, this is not necessarily specific to main memory. You could have a hybrid cache design as well, right, if you think about it. And there are similar trade-offs you can potentially make. But we're not going to go into the cache design. We're going to look into the main memory design, part of which could be a cache. So one question is, what is cache and what is main memory if you have this off-chip hybrid memory system? We're going to talk about that a little bit. What is the granularity of data movement or data management? Is it coarse? Is it fine? Is it at the page level? Is it at the cache block level? There are upsides and downsides to this, especially when you're designing a huge cache. Who manages different portions of memory? Is it the hardware? Is it the software? Is it cooperative? Cooperative is usually a good answer, but it's good to partition the duties nicely between hardware and software. But sometimes software management, pure software management, is not easy, especially if you want to move data frequently between two memories. When do you migrate the data between the two memories? And how do you migrate the data? And how do you, if you want to use one of the memories or a portion of one of the memories as a huge cache, how do you design it to be scalable and efficient? Because a cache always has the overhead of a tag store, metadata overhead. Where do you store that metadata? How do you manage it? It becomes actually complex with very large caches. If you want to store it on the processor chip, it adds a lot of complexity into the processor chip. So we will see that in a little bit. There are many other questions that we're not going to be able to cover. I'm going to cover a subset of these. And clearly, I'm not going to be able to go over the entire design space, because it's an area where there's a lot of ongoing research at this point. But it's clear that we'll have some sort of hybrid memory going into the future. This exists already in the GPUs. This is going to exist more and more in the systems that we have in general purpose as well. Okay, so one option that we're going to look into is using DRAM as a cache for PCM. In this case, PCM is main memory, and DRAM caches memory rows or blocks. The benefits is you get reduced latency and reduce energy also on a DRAM cache hit, and you can actually buffer the writes in the DRAM, because DRAM doesn't have an endurance problem. It doesn't have a write energy problem. It doesn't have a write latency problem. That sounds good. Basically, DRAM is a huge write filter for phase change memory. Now, this alleviates a lot of the issues that we discussed earlier, right? It's not easy to design a phase change memory chip that internally does this caching, but if you have a DRAM chip that does the caching for you very well, a lot of the downsides of phase change memory doesn't get exposed to the system. Okay, and we're going to look at memory controller hardware managing the DRAM cache. This eliminates the system software overhead, because if you want to move a block from phase change memory to DRAM, and if you have to invoke software to do that, that takes a lot of overhead. And we're going to see that overhead later on when we talk about persistent memory. But even with non-persistent memory, in this case, we're not going to exploit actually the persistence, non-volatility properties of phase change memory. That's a separate discussion that we will have. But if you actually have to invoke software every time when you want to move data between two very, very fast memories, that software overhead dominates. As a result, it may not be very good system design. Actually, people find this out in Flash, for example. Whenever you want to access Flash, you go through many, many layers of software today. File system layer, and there's system calls. There's buffering that happens in DRAM, for example. But that many layers, as a result, you don't get the full bandwidth and the low latency of the device. Because now you need to go through this huge software layer, which takes some time. And then there's a device latency. So the device latency is relatively low, but the software layer's latency is very high. So people have actually tried to make the file systems a lot leaner, and the operating system calls that are needed to access the file system a lot leaner, such that you could get the best out of these flash devices. And there's a lot of work in that area, actually. And they basically say that we want to get rid of the software as much as possible. Because this device actually is very capable of doing very high bandwidth, a low latency access, that the software is actually limiting the access rate. Okay. So it's going to be much worse with a technology that's much similar to DRAM, right? Okay, so there are 3 issues that we're going to discuss. This is not the only 3 issues, but 3 things are interesting, certainly. What data should be placed in DRAM versus kept in phase change memory? Basically, what should be cached and what should not be cached? I mean, there's a general caching question that we covered, of course. We're going to look at it from the specific examples over here of emerging technologies. What is the granularity of data movement? And how do you do it? And how do you design a low-cost hardware-managed DRAM cache? And there are 2 idea directions that we're going to talk about. One is locality-aware data placement, and the other is cheap tag stores and dynamic granularity. And I'll give you some other ideas along the way also. But I'm not going to be able to cover everything comprehensively because there's actually a lot of work in this area. Some works, for example, which I will touch upon, propose using the virtual memory management schemes and using that as a way of managing your cache. Basically, whenever you do the virtual to physical address translation, you also store some bits saying that, oh, this address is actually inside your DRAM cache or not, right? And that's actually nice because now the overhead of keeping the tag store is part of your virtual memory system, and you do the translation all the time, so you get that for free almost. You don't need to have a tag store, or in other words, your tag store is now inside your virtual memory system. But that causes some other issues also. Whenever your mapping changes, now you need to change your page table perhaps, right? Or wherever you store this. Okay, so basically there's actually a huge design space over here. But let's talk about DRAM as a cache for PCM. As I said, after we presented the paper at ISCA in 2009, there was also this paper presented in ISCA 2009. They were both looking at phase change memory. We were looking at it from a very different perspective. We were trying to enable the same in the end, but this paper actually had more optimistic results because it took into account potential capacity benefits as well. So we will take a look at it. And it also actually tried to have both DRAM and phase change memory in the system. So basically, we would like to achieve the best of both DRAM and phase change memory, or some NVM. And of course, DRAM is not very scalable, so we'd like to minimize the amount of DRAM without sacrificing performance and endurance. So how do we achieve this? Well, one way of doing it is having DRAM as a cache to tolerate the phase change memory latency and write bandwidth and endurance issues. And phase change memory is the real main memory that's exposed to applications. It provides large capacity at good cost and hopefully power, right? So basically, the system looks like this. You basically have a hybrid memory system before flash or hard disk drives over here. So you have a DRAM buffer, and DRAM buffer actually, it's essentially a cache, so there's a tag store associated with it. We're going to look at the design of it later on. And then a write queue over here. Okay. So how do you actually manage this DRAM buffer? There are some ideas over here. Basically, one is the idea of lazy write. Which means that whenever you bring a page from the disk system, you directly put it into DRAM and not phase change memory. Now this actually saves the limited number of endurance cycles that you have in phase change memory, right? You don't write to phase change memory as often because it's precious. Every write is precious to this, so you directly put the data over here. That sounds good, right? The other idea is very similar to what we earlier described. Basically, partial writes. Only the dirty lines from DRAM get written back to phase change memory. You don't write the entire page, basically, which makes sense. And even within the dirty lines, you can actually do the optimization that I just discussed, right? Only the dirty words you can put in there. And there's another optimization, which is called page bypass over here. Essentially, they discard pages with poor reuse. So whenever you're evicting something from DRAM over here, you have a reuse predictor somehow. It's not described a lot, but you can imagine what that could be, right? And based on that reuse prediction, you either write back to phase change memory or discard the page, right? That's the idea. Or if it's a dirty page, you write it back directly to flash, right? So that's the idea over here. If you don't have good reuse, you don't want to write back to phase change memory. So the principles, high-level goals are the same. If you have phase change memory, you don't want to write to it much, and you don't want to read from it much. you want to minimize. But it is there hopefully to buy you a lot of capacity, and when you need it, you read from it. Okay, so let's take a look at the evaluation of this paper, because this is a more system level evaluation. As I said, it's a more optimistic evaluation because what it assumes is, it assumes phase change memory is denser, 4x denser, which means that the capacity that you would get for the same cost is 4x of DRAM. In that case, of course, you buy a lot more performance, right? Well, we'll see how much. The assumptions are a little bit different. So we assumed, for example, phase change memory is, in terms of reads, it's a 4x slower than DRAM, though that's similar. But for us, writes were asymmetric, which is really true in existing phase change memory systems. So we said writes are 12x slower. And this paper assumed that they're also 4x slower. That's okay. Basically, they're going to alleviate some of those writes with the DRAM. This is not working very well so far. So here's when redundancy helps. But this is not a very reliable one, because it's not very easy to use. Something happened. Okay, that was not a bad switch. Okay, now it's working, but it's a bit smaller. Okay, so basically what they did was they simulated a 16-core system with 8 gigabytes DRAM memory and some cycles. You can take a look at it. It was a more probabilistic simulation that they assumed a flash hit rate of 99%, for example. And these were the hard disk parameters and flash parameters. As you can see, it's 2 milliseconds to access the hard disk and 32 microseconds to access the flash. So I like the simulation methodology in this paper, because if you want to do this sort of simulation, you cannot do a cycle accurate simulation. You need to be probabilistic, and you need to basically cut corners in the simulation to get the results. It's not, if you're cycle accurate, these simulations will run forever, as you can see, right? Because you're simulating a 2 millisecond access to hard disk drives. Okay, so let's take a look at the results. So this is geometric mean across some applications that IBM was interested in. At that time, you can see some interesting applications like databases, quicksort, clustering, blah, blah. Basically, this is the baseline system. It's an 8 gigabyte DRAM system. And this is the equivalent system. You have a 32 gigabyte PCM. They assume that it's equivalent in terms of cost. And if you compare those two, this is the execution time. 8 gigabyte DRAM is here. 30 gigabyte PCM directly improves performance, which makes sense because you have a lot more memory in the system. You get rid of essentially accesses to flash, a lot of access to flash. Now let's take a look at the more interesting comparison, perhaps that's similar to what we have done, which is 32 gigabyte PCM and 32 gigabyte DRAM. So if you look over here, 30 gigabyte PCM is over here, 30 gigabyte DRAM is over here. So clearly 30 gigabyte DRAM is much faster. Maybe it's not as fast as what we have seen because our latency parameters were more pessimistic. But it's also makes sense, right? If you actually add phase change memory into the system, the same amount, replace DRAM with phase change memory, you lose performance. That's what the blue bar says compared to green bar. Now this is the hybrid memory system, which is 32 gigabyte PCM and 1 gigabyte of DRAM. Managed the way that I described in the previous slide. If you do that, now you get much closer to 32 gigabyte DRAM, right? Basically, you're much better than 32 gigabyte PCM because DRAM actually alleviates a lot of the issues with PCM. You're not as good as 32 gigabyte DRAM because most of your memory is phase change memory and only a little of it is DRAM. But you're close enough. And that's the idea of a hybrid memory system. How do you get close enough over here? That sounds good, right? Basically, this is how you can enable a new technology in the short run, in my opinion, by taking advantage of hybrid memory technologies. And maybe you can actually do even better by managing the DRAM better, right? Maybe you can get even more close to the screen bar over here. Sounds good? Okay. So then this paper also had some evaluations in terms of power and energy. And if you look over here, you get significant energy savings with a hybrid memory. I think this is power. Of course, the power of hybrid is higher than 8 gigabyte DRAM, but lower than 32 gigabytes of DRAM, as you can see, as expected. And this is the energy. Energy of hybrid is much better because you get performance improvement also, and this is the energy delay product, as you can see. And this paper also showed that the average lifetime of this memory is about 10 years. which is good because you have a huge DRAM buffer, ensuring that you don't have an endurance, not ensuring that, but reducing the endurance problem. But as you can see, there's still an endurance problem. 9.7 years is not infinity. You need to write to PCM at some point. And there are no guarantees. Again, some applications can actually circumvent the DRAM buffer somehow, and as a result, they can destroy your memory faster. But this is also very promising. I think hybrid memory systems are very interesting because of these results. So if you want to read more, this is one of the papers from IBM at that time. Okay, so let's talk about data placement. Any questions so far? No? Okay. Let's talk about data placement in hybrid memories, because it's a general problem. It's not just about emerging memory technologies. It happens whenever you have hybrid memories that look like this. You have some memory, and I'm going to abstract it as fast and small right now. And you have some other memory that's large and slow, and they're at the same level. What do you place where? Right? Let's assume that you're doing page level management. You need to move the page. Now, one downside is it consumes a lot of bandwidth to move the page, and you want to maximize system performance. And there's also another issue over here, which is while you're accessing, assuming that this is a fast memory, yes, maybe you would like to access this memory as much as possible, but that may not be the right thing to do, even if you have extremely good caching benefits over here, because if this memory is sitting on another channel, it becomes idle now, right? You maybe reduce latency, but you may be actually creating a bandwidth bottleneck on this channel. So there are multiple considerations that you need to have in this sort of system. Maybe you should balance the load better across the channels, as opposed to, so it's not a simple caching problem as before. If you have a caching problem, maybe you actually put the stuff that, basically you may want to get the best out of your cache over here. Here, if you actually put everything into your cache, and you have an extremely good cache hit rate, 100% over here, what does this channel do? In this particular design, right? You have a load balance problem. Now there are of course other potential solutions. Maybe you have another channel over here that's connected to memory B. Then that becomes more like a regular caching problem, but that has its own downsides. So there's a huge design space over here that we're not going to cover. And page migrations clearly have performance and energy overhead that you need to think about. So I'll give you a couple of ideas over here. One of the ideas over here, again, is relatively simple. We'd like to characterize the data access patterns somehow, either in software or hardware, and guide data placement in hybrid memory. So one example is, if you look at streaming accesses, if you're streaming through memory, always accessing the next cache block, these could be as fast in phase change memory as they are in DRAM. This is really dependent on how fast you can move data out of your row buffers. They're really independent it's really independent of the technology, if you think about it, because the data is coming out of your SRAM in this case, if you're designing the system well. So you can make it as fast in phase change memory as in DRAM. Well, this is also going down, but that's okay. But if you look at random accesses, meaning that whenever you need to access the array, they're much faster in DRAM because the array is much faster in DRAM. So if you know this characteristic, now you can actually design a data placement policy that's relatively simple. You categorize your data somehow. You place data that you access randomly with, in a random access manner, with some reuse, of course, in DRAM. If you're going to access it again at some point, you'd like to put it in DRAM. Otherwise, you put the streaming data in phase change memory. Hopefully this makes sense. Right? Because if you want to keep in DRAM the data that is going to be reused, and you want to, you're not going to get the same benefits, and where DRAM is useful at, meaning DRAM is going to provide low latency. I'm going to go into this in more detail. Whereas if you're streaming, if all you're doing is streaming in a system, your memory system should be just optimized for streaming bandwidth, right? And streaming bandwidth is relatively easy to handle because, as I said, you could do buffering, right? And SRAM buffers can deliver you very high bandwidth. In this case, maybe the technology that you have, underlying technology that you have, doesn't matter. Maybe you have a tape, and that tape gives you initial very high latency. But since you're streaming the data out of the tape, you just need enough buffering such that you get high bandwidth, right? That's the idea over here. So when you're doing streaming video, for example, maybe you don't need extremely expensive memories to stream the data. Your initial latency, as long as you can tolerate the initial latency of access, you just keep streaming from a very slow technology. So when you're serving videos on YouTube, maybe you don't want extremely high capacity DRAM in your system, except for buffering maybe. Okay, so this is the key observation. Basically, the key observation is that row buffers exist in both DRAM and PCM. As a result, row hit latency is similar in DRAM and PCM, and row miss latency is small in DRAM, whereas it's large in PCM, because the array access latency is much larger because of the technology in PCM. And we would like to place data in DRAM that has two properties. One is that's likely to miss in the row buffer, which means that it has low row buffer locality, which means that it's relatively random access, right? And the miss penalty, because the miss penalty is smaller in DRAM in this case. And the second property is data that is reused many times. We would like to cache only the data that's worth the movement cost and the DRAM space. You may actually miss in the row buffer once and twice, and that's it. You don't access that row again. You don't want to move that data from phase change memory to DRAM because you're not going to access it again, right? So you need to take into account reuse as well as the access pattern. Now, who does this? Basically, in this work, we actually designed a hardware memory controller algorithm, but potentially in the software, you can mark your access patterns this way as well. So it's a general idea. Who does this, I think, is open still. And you can use pragmas to annotate your access patterns, for example. Okay, so what is the benefit of this? This is actually very, again, relatively pessimistic simulations, very intense workloads. And we're going to assume 16 gigabyte PCM over here and 16 gigabyte DRAM. And this is a hybrid system, and I don't remember the parameters of how much DRAM and how much PCM, but it could be 1 plus 16 or 1 plus 15. I don't remember. You can take a look at the paper. 1 meaning DRAM is small. So if you actually look at 16 gigabyte PCM over here, 16 gigabyte DRAM, average across many, many workloads, 16 gigabyte DRAM system is much faster, more than 80%, as you can see over here. If you use this hybrid memory management, we get somewhere in between. So it's not as optimistic as the previous paper that I showed you. It's a little bit more pessimistic because the parameters are much worse, actually, especially the write parameters in this case. And that's not bad, but this means that there is still a gap between a hybrid memory system and a DRAM system. And how do we cross that gap? Basically, there needs to be more ideas, more algorithms to be developed. And you can read the paper for the fairness results. Oh. Okay. Any questions? I give you just one of the ideas, example ideas. There are many, many more in the literature. No questions? Okay, so let me give you a couple of other ideas over here. So one of the issues with this sort of memories is heuristics, right? You actually have a lot of heuristics to manage data. I give you one heuristic as an example. Actually, that paper, I didn't talk about this heuristic, but that paper also takes into account write latencies and write endurance. So it's not just row buffer locality and reuse, but you need to take into account write latencies, write endurance, and in the paper there is a model that talks about, okay, this is how you take into account writes, but it's a lot of heuristics in the end, so it becomes a little bit hard to manage. So we wanted to actually have a model that's much better, more comprehensive. And I'll give you some ideas related to this. I think there's more work to be done in this case. Basically, these heuristics consider a limited part of memory access behavior. They do not directly capture overall system performance impact of data placement decisions. Ideally, you have some number of decisions to make, and each decision has some performance impact, and you would like to predict that performance impact early on. Maybe there's a case for using machine learning techniques over here, actually. We haven't looked at it, but I think that this is another example of where machine learning can actually very nicely fit how you can manage existing systems. Because I think here, again, the memory control has a lot of data that it can deal with. It just needs to make sense out of it. And humans, as we're going to see, may not be very good at considering all of the characteristics, again. And whenever we're designing something, we're going to have a fixed policy, whereas a machine learning algorithm can actually change its policy over time, like we talk about with the reinforcement learning controllers. So I think there's a very good opportunity over here also in terms of machine learning, but that's not what I'm going to talk about. I'm going to talk about a human-developed model that tries to predict the performance impact of data placement decisions. And also I'm going to talk about memory level parallelism. Basically, we talked about memory level parallelism. Different cache misses have different costs right? Because they may be overlapped with other cache misses, or they may not be overlapped with cache misses. And that's also important in this case, because that affects your benefit significantly. So basically, the number of concurrent memory requests from the same application when a page is accessed, that's the memory level parallelism, it affects how much page migration helps performance, actually. It's very similar to what we discussed in MLP-aware cache replacement, but in this case, the effect is much larger because you're migrating a huge page, assuming you're managing things at a page granularity. Okay, so let's take a look at it over here. So let's assume that you have request to page 1 over here, and from the slow memory. If you migrate it to fast memory, the requests to page 1 are serviced much faster. You save time t. Clearly, that makes sense, right? Migrating one page reduces stall time of an application by t. But let's assume that the application has 2 requests. One request to page 2 and one request to page 3. And you decide to migrate only one to fast memory. You don't gain anything, right? This is classic memory level parallelism because the application needs both pages. I shouldn't say page A and B. This is fast memory. This is slow memory. Or the other way around. This is slow memory. This is fast memory. And basically, both pages are in slow memory in this case. You migrate only one to fast memory, and you don't gain anything, right? Because the application needs both of the pages to proceed. In this case, in order to gain something, you really need to migrate both to reduce stall time by t, just like over here. And t is the difference between the access time of both memories, assuming everything else is equal. So migrating one page alone doesn't help, so you need to migrate 2 pages. Of course, if you're waiting for 5 pages together at the same time and you need to be able to have all of them to proceed, then you need to migrate all of them, right? Now clearly the number of migrations you need to do to reduce the stall time changes depending on the memory level parallelism patterns of an application. Now this complicates a lot of things. And this affects things a lot because there's a huge, imagine it's a 4 kilobyte page that you're moving between this memory to this memory, right? That's a lot of data movement. So page migration decisions need to consider memory level parallelism. But they also need to consider robot for locality. They also need to consider application level impact in terms of performance. They also need to consider writes, like how many writes you do, write endurance, and they also need to consider reuse, right? So they need to consider a lot of things actually. That's why I believe this is a very good fit potentially for machine learning techniques that can keep the human sane or saner. Basically, but what we wanted to do in this work is to have a generalized mechanism that first can directly estimate the performance benefit of migrating a page between any 2 types of memory. That's the goal. If you have a generalized mechanism, that's nice, right? And the second is that places only the performance critical data in the fast memory. That's the hope. Now it may not be easy to do it, and the model we developed is better than previous models, but it's not necessarily the best thing that that you can have. For example, it doesn't fully consider the load balancing decisions between different channels, right? That's another thing to consider, but it's not very easy to consider always. And that's very dynamic as well. Okay, so the idea, I'm going to sketch the idea. It's called utility-based hybrid memory management. Essentially, the goal was to have a memory manager that works for any hybrid memory, DRAM, NVM, DRAM, PCM, DRAM, reduced latency DRAM, different types of DRAM. And the key idea is for each page, we use a number of characteristics, they're called comprehensive characteristics, to calculate an estimated utility or the performance impact of migrating the page from one memory to the other in the system. So what is the utility of migrating this page from here to here? That's the first thing. If you estimate that accurately, you're some steps there. But that's not enough because you need to then migrate only pages with the highest utility, pages that improve system performance the most when they're migrated. Okay. So let's talk about this. Basically, for each page, you estimate the utility using a performance model. You migrate only pages whose utility exceed the migration threshold from slow memory to fast memory. And you periodically adjust the migration threshold because it turns out this changes over time. And because applications change behavior over time, right? So how do you actually estimate the utility using the performance model? Basically, we would like to look at figure out what is the application stall time reduction because we migrate this page from this memory to this other memory. Basically, how much would migrating a page benefit the performance of the application that the page belongs to? That's one aspect of the equation. That's not enough, because there are other applications that are running in the system potentially, right? Or other threads that are running in the system. So you need to also look at the performance sensitivity of the application. How much does the improvement of a single application's performance increase the overall system performance? So this application may benefit a lot from this, and as a result, system performance may improve a lot. But another application that may not have a lot of effect on the system, overall system performance, right? Because these applications have different characteristics. As some applications that are more compute bound, if you actually migrate their pages to fast memory, you ensure that they make fast progress in the system. And as a result, they have a lot more benefits because they keep their cores busy. But if you have an equivalent application that's not compute bound, that's memory bound, you migrate this page to the fast memory. But this application, yes, it becomes faster, but its benefit on the entire system performance may not be a lot, right? That's the idea over here. So basically, utility is defined in this work as how much does the stall time of this application reduce times the sensitivity of the entire system performance to the improvement in this application's performance. And you can read the paper for more detail. And again, you can poke a lot of holes into the model because there's a lot more to look into in this. It's not easy to do this performance model. Okay, so let me give you the key results. This is actually better than all of the previous mechanisms that we described. And I haven't described everything over here, but basically this is the weighted speed up compared to 3 different mechanisms. RBLA is what I just described earlier, robot for locality aware management that takes into account robot for locality and also reuse as well as write intensity of an application. And for the full mechanism, you should read the paper that I briefly described. Frequency-based management, basically it tries to figure out what are the frequently accessed pages using a probabilistic method. Probabilistically, it determines which ones are the frequently accessed pages, and if a page is frequently accessed, it gets migrated to the fast memory. It's relatively simple, but as you can see, it doesn't buy the best performance. And all means actually all pages get migrated to the fast memory. So it's not very good, as you can see, especially when intensity of the applications is high. This basically categorizes applications based on how intense they are in terms of their accessing memory, and higher intensity means that they have a lot more access to memory, and lower intensity means that they have a lot fewer accesses to memory. So as you can see over here, now this utility-based management actually buys significant performance improvement compared to the best previous mechanism. As expected, but it's more complex also. Okay. And actually, this is a relatively general mechanism. So this is something that's interesting. I think that all papers going forward really should do, in my opinion. Basically looking at different types of memory. So we said fast memory versus slow memory. The question is, how good are the mechanisms when the distance between fast memory and slow memory increases or decreases? So basically, this is the latency multiplier of the slow memory. In this case, the activate and write latencies are 3x longer than the fast memory. In this case, it's 4x. In this case, this is very similar to the phase change memory-based system that I just described, right? 4.5x and 12x. In this case, the activates are 7.5x slower and writes are about 20x slower in these latency parameters. Of course, it's good to do the study, right? That's very comprehensive, but it's very hard to simulate every possible configuration. But this is interesting because, I mean, at least it turns out this mechanism is actually more powerful when the reads and writes are more asymmetric, because it takes into account some of that asymmetry implicitly in the memory level parallelism and explicitly in the write intensity. If the reads and writes are symmetric, some of the previous mechanisms get closer, but that's also a potential. But there's more to explore over here, basically. Hopefully this gives you an example of the complexity of the problem also. Okay. Any questions? I think I've given you a lot of ideas very densely. But there is a lot more work to do in this area. Actually, I'm fascinated by the potential of using machine learning techniques that has not been explored, for sure. As far as I know, I haven't checked the very recent papers. Any questions, thoughts, new ideas? Okay, so basically I've given you some examples on enabling and emerging technology to augment DRAM in this case, right? Before we were trying to replace DRAM, now we're trying to augment DRAM. We want to actually minimize the DRAM as much as possible because of scalability issues. But again, what I just described could be applicable to two different types of DRAM also. So it's good to develop models that are more agnostic of the technology as well, because then the models are applicable directly to any hybrid memory technology, right? And we need to manage hybrid memory somehow. Now let me switch gears and let's talk about a related direction that is essentially orthogonal. We've talked about using phase change, using DRAM as a cache for phase change memory, but there's a problem here. In addition to the problem of what you should put into that cache, there's a design problem in terms of how do you actually design this very large cache. It could be DRAM in this case, but it could be any cache actually. And there are many recent works in this area that I'm not going to cover in detail, but we're going to first start with the problem. So what is the problem? Basically, whenever you have a cache, you need to have metadata. Metadata means tag store, right? There's a data store and a tag store, as we've covered in the first lectures. And this tag store is essentially metadata. It's useful to access the cache, but essentially it's overhead, right? You need to have that tag store so that you can access the data. And the problem is that a large DRAM cache requires a large metadata store, tag plus block-based information store. The key question is how do we design an efficient DRAM cache? So basically, if you look at what we're trying to do, assume that we have a system that looks like this. You want to load X, you missed in the cache in the CPU, and now you need to consult some metadata that tells you where that X is. Let's assume that the metadata is in the memory controller somewhere. Metadata says X is in DRAM. Then you access X from DRAM, bring X, and then bring it into the CPU hierarchy and read it. Okay, so where does that metadata sit? One option for that metadata is to have it in the memory controller, right? Have a big SRAM store, SRAM tag store. Now let's do the calculation very quickly. If your DRAM is 1 gigabytes, 1 gigabyte is how much? 2 to the 30 bytes, right? That's small. Okay, 2 to the 30. If it's 2 to the 30 bytes and your cache block size is 64 bytes, 2 to the 6 bytes, now you have 2 to the 24 tag store entries, right? For each block, basically. And 2 to the 24 is already a big number. Assume each tag store entry is 4 bytes, that's 2 to the 26 bytes. That's 64 megabytes already. That's already bigger than your last level cache almost, right? That doesn't sound good. Maybe you should not do this and have a bigger last level cache. So that basically that's the problem. And if you actually have a 4 gigabyte DRAM, then the problem multiplies by 4 in that case, right? So essentially, where do you put that metadata? Putting it in an SRAM store over here is too costly, expensive, and there are also scalability issues like what we've discussed with Raider early on, right? Let's assume that you put a 64 megabytes tag store over here. That's good. That works for 1 gigabyte DRAM. But somebody wants to plug out that 1 gigabyte DRAM and put 4 gigabyte DRAM. Now your tag store is not enough. It's all gone, right? It's not scalable. Okay, so that's the idea. So how do you actually do this? So I'll give you several ideas. One idea that's relatively commonly employed today is to store the tags in the same row as data in DRAM. Basically, DRAM row, if you look at it, is partitioned into data and metadata. And metadata is stored in the same row. And this means that data and metadata can be accessed together, meaning whenever you open a row, you get the metadata first, tag store, you check the tags, and if there's a tag match, you get a row hit on the data. That's the idea. And this makes sense. Actually, I didn't give you idea 0, which is tags in memory but not in the same row. So you could have tags in some other parts of memory, and basically you can partition your bank, let's say. Part of it is data, part of it is metadata. You first access the metadata. You check whether you have a tag match. Assume that you have a hit. Now you access the data in some other row. That's not terrible, but as you will see, that the performance of that is not good because you're not exploiting the row buffer locality. Here you're exploiting the row buffer locality. If you get a hit, your cache block, the data is actually a row buffer hit. You could actually potentially prefetch it early on. Okay, so that's the first idea. Hopefully that's clear. So the big benefit over here is now you've gotten rid of the on-chip tag storage overhead. That 64 megabyte that you need on chip for the tag store goes away. because you're really storing the metadata inside the DRAM itself. Yes, you're losing capacity inside the DRAM, but that capacity is a lot. You already have, let's say, 1 gigabyte and 64 megabytes of it, plus some overhead because you may not be able to align things nicely in the row, plus some overhead goes to the tag storage space. So maybe, hopefully it's not that large. Of course, there are other downsides aside from the storage overhead. Now your cache is determined only after DRAM access. You need to access this row to get the tags and then do the tag match, which means that you need to do a DRAM access first to get a cache hit or miss signal. And a cache hit, as a result, requires 2 DRAM accesses. You first need to check this. First access, probably a row buffer miss or conflict. And the second one, hopefully a row buffer hit, assuming it's a cache hit. And you get 2 DRAM accesses. That doesn't sound good. So we'd like to improve it. How do you improve it? Well, caching. Basically, what you can do is you have these tags in DRAM, in memory. You can cache some of them. No, that's what, basically that was the first idea, tags in memory. But you can cache some of them in on-chip SRAM. So which ones do you cache? You access the frequently accessed ones, basically. So that's the idea. You cache only a small amount to keep the SRAM size small. So now the SRAM that you keep in the memory controller is not for the entire tag store, but it's only a cache for the tag store. It can be very small, and you will see the results with a very small cache, tag cache. You can actually get a lot of the benefit. So it sounds interesting, right? We're putting layers of caching. So this is really a cache that's there to improve the performance of the cache. So you're really caching the tags. It's actually a relatively old idea. It's not whenever you think about caching tags, it was proposed as early as 1995. There was a paper from Hong Wang, actually, is the person who proposed it. They basically wanted to reduce the on-chip access rate. So if you want to build a large cache on chip, your tag store access time is relatively slow. So they actually said, oh, we can cache some of that tag store on chip again so that we can access it fast. So that idea essentially gets applied to the outside over here. But of course, there's a bigger benefit, I think, here, because now you don't need to build a huge tag store on chip in this case. Okay, so that's the second idea. We're going to examine the benefits. And there's an orthogonal idea which deals with the other thing that I mentioned earlier, which is what is the transfer granularity? Actually, this is interesting. This is an area that's not explored as much. We assume so far, for example, you transfer at the page granularity, but that may not be a good idea. That's also true for SRAM caches too. It may not be a good idea to always have a fixed granularity access, because some applications benefit from caching more data. They have good spatial locality. Others do not, clearly. As a result, if you actually have large granularity, you waste bandwidth, and you actually reduce cache utilization also, because you're caching these huge 4 kilobyte pages, and the application is using only 8 bytes out of the 4 kilobyte pages, right? That doesn't sound good. If you have fixed granularity, you have no choice. If you have very good locality on those 8 bytes, you'll bring the entire 4 kilobytes because you have fixed granularity in your cache, right? That's why you shouldn't have fixed granularity in your cache. So basically, this third idea is to have a simple dynamic caching granularity policy. I'm not going to go into the detail of it, but essentially, there's a cost-benefit analysis to determine the best DRAM cache block size that the DRAM cache should follow. And we're going to use the idea of set sampling that we discussed much earlier in the lectures. You group main memory into sets of rows. Different sampled row sets follow different fixed caching granularity. Some of them, for example, cache data at 4 kilobyte granularity. Some of them cache data at 64 byte granularity. Some of them 256 byte granularity. But only small sampled row sets. And the rest of main memory follows the best granularity. So how do you do that? Basically, you do this cost-benefit analysis. These sampled sets follow the fixed granularity, and you look at which one's doing better. It's basically the hybrid cache, very similar to hybrid cache replacement and management policies that we've discussed in the past using set sampling. But of course, the parameters are different, and you don't need to remember exactly how it is. If you're really interested, you can read the paper. And it's performed once in a while so that you change the caching granularity once in a while the programs are running, while the system is running. Okay, any questions? Okay, so this is called timber in the end. Tim means tags in memory, and I don't know what bear means, but timber sounds good. Essentially, let's take a look at the results. So this is average across many applications. You can read the paper. This is an SRAM tag store. It's huge. It's not very efficient, as we will see in the energy results. This region-based tag stores is what I described as idea 0, meaning you divide your bank. Part of it is for tags, part of it is for data, and you first access the tag space to get a hit-miss signal, and if you get a hit, you access the data space. So they're not in the same row, tags and data. And as you can see, the performance loss compared to having a tag store that's on chip SRAM is huge. You basically are slower by 2x, right? If you interpret this data, that's 0.5x, you're slower by 2x. That doesn't sound good. So let's put tags in memory, except we do it such that the tags are in the same row as the data. That buys you a lot of performance, as you can see over here. Now, if you actually cache the tags on chip with a small SRAM tag cache, you buy a lot more performance. Now we're getting actually very close, right? This is about 85% or so. And we're within 15% of a huge SRAM tag store without the energy overheads, as we will see in a little bit. So of course, Timber itself can be improved. There are some ideas that we haven't looked into, but others have looked into. For example, you could prefetch the tags early on. Now you're actually using these mechanisms that we use to reduce memory latency to reduce access latency to the cache tags, right? This is why I think fundamentally changing the paradigm can help. Meaning, if you do processing in memory, maybe you don't have a lot of these other complexities that we discussed earlier, right? But whenever you have this sort of caching, you actually need to improve the performance of caching as much as possible. It's very interesting, but maybe it's not. Maybe it's fundamentally broken, right? As we discussed in the last lectures. So keep that in mind. But of course, these ideas have benefits potentially in processing in memory also. Okay, so basically, you can perhaps close the gap even better if you actually design this even more seriously. Maybe you get to 95% over here. That's fine. So there's an orthogonal thing over here, which is a dynamic caching granularity, which could be applied actually over here as well, but we didn't do that. That's our fault. So basically, if you actually use dynamic caching granularity on Timber, you gain even more performance, right? But if you think about it, dynamic caching granularity idea that I just described has nothing to do with these. It's orthogonal to these, and it could actually be applied in SRAM cache, so it could actually improve performance by a similar amount over here. Okay, that's performance. So this is what you get by managing your cache better. You avoid the huge SRAM on chip. And the energy is actually pretty good. So this is, with a huge SRAM, this is the energy you have. If you do region-based, actually your performance per watt, this energy efficiency actually, reduces because you lose performance, but maybe your energy is not that bad. Remember, performance loss was about 50% over here, but performance per watt loss is actually not terrible. So because this huge SRAM on chip actually consumes a lot of energy also, that didn't exist in the baseline, right? Okay, and then with tags in memory in the same row, you actually get better energy efficiency, and by caching the tags intelligently with a small structure, you get a lot more energy efficiency. Again, you're closing the gap, as you can see over here. This is about 90% compared to SRAM tag cache. And if you actually do the dynamic caching granularity, that buys you a lot over here because you have fewer migrations of transmitted data, right? You don't always do 4 kilobyte caching granularity. Sometimes you do 64 bytes. And as a result, you actually get rid of a lot of unnecessary data movement. That's why this energy efficiency shoots up over here. You gain both performance as well as you reduce energy because you don't do unnecessary data movement. So that's another attestation to the fact that data movement is a huge energy consumer. Basically, you want to get rid of that as much as possible. Oh, okay. And this is the paper that described a lot of the ideas, and it's only a very short paper actually. Okay, let me see. Actually, let me cover a little bit more on the DRAM cache, and then we'll take a break. Basically, I'm not going to go into this, but this is one of the most recent, actually one of the most state-of-the-art works as far as I know. We published this in Micro in 2017. It actually covers a bunch of different schemes that were proposed, and if you're really interested, you can take a look at them. This work is called Banshee, and of course it's all green, as you can see. But of course, we know its downsides, and it's also mentioned in the paper also. But basically, the schemes can be classified in terms of how you do the DRAM cache hit, how you handle the DRAM cache miss, what kind of latencies do you get, what kind of traffic you impose, what kind of replacement traffic do you cause on the system, do you cause it on every page, who manages it, what kind of replacement decisions do you make, who manages it, and are you able to do cache large pages, for example. Of course, you can extend it more, but this is what we were interested in at the time. Clearly, there are trade-offs over here. And this paper is interesting because it's actually using a software-hardware cooperative mechanism. And I think this is actually very interesting to look at going forward. It tracks presence in a DRAM cache by using the TLB and the page table. Meaning that you don't need a tag store right now anywhere except for the TLB and the page table, right? And the problem right now is whenever you actually change the contents of the DRAM cache, you need to change the page table and the TLB. And how do you do that? You need to have an efficient mechanism for that, because that TLB entry can be cached anywhere in any TLB in the system. So you need to actually ensure that you get a TLB, you keep the TLBs coherent, and ensure that you basically shoot down the TLB entries or invalidate the TLB entries that are stale whenever you change the mapping. That's the idea. And how do you do that? You should take a look at the paper. It adds some support, hardware support in the memory controller to minimize these shoot downs and make sure that they're efficient. And also there's another completely orthogonal idea that basically tries to reduce the data movement. Basically, it's a bandwidth-aware, frequency-based replacement policy that tries to minimize the cache replacements. And you can take a look at the paper, but essentially it performs well. These are the other caches. Some of them are completely software managed. If you can go back over here, this is basically completely software managed, for example. And hardware-software cooperative solution is actually better than the software managed versions. But I'm not going to go into the detail of this because there's a lot more work that we will need to open up if we actually want to go into more detail. And I'm already running pretty late, I think. So where are we right now? Okay, 14:23. Any questions? But I just want to give this to you because actually this enables, there's another aspect of it, which is the hardware-software cooperative management. Okay, I think it's a really good place to take another break. How about we come back at 2:35? Okay, let's continue. We're going more slowly than I expected. But hopefully it's interesting. Is the good pace? Okay, good. So hopefully we'll finish off emerging technologies today. Even though you may not be able to finish off all the slides, I'll give you the gist of the ideas at least. But there are a bunch of other opportunities with emerging technologies other than replacing DRAM. I think there's a lot more. And we're going to talk about one of them over here. One is merging of memory and storage. Basically, can we have a single interface to manage all data as opposed to different interfaces that we have today? I think this is fascinating. In my opinion, this needs to be done. Maybe even with the flash technology, but we can talk about it. The second is new applications. Of course, we didn't talk about applications a lot here. What kind of applications do these technologies enable? People have been talking about ultra-fast checkpointing and restoring, very fast boot up. Of course, these are maybe easily imaginable things, but what else can you do? It's good to always think about applications. More robust system design, how can you reduce data loss? If most of your system has persistent memory, how can you take advantage of that? If your caches are persistent, non-volatile, how can you take advantage of that? How does system design change if all of your memory is persistent? I think there's a lot to think about over here, and part of the rethinking is over here actually. And finally, as I mentioned, processing tightly coupled with memory is potentially a lot more powerful if you have an emerging memory technology for two reasons. One is, as I said, these emerging memory technologies are resistive. As a result, reads are not destructive, so you don't fundamentally need to move data to operate on the data, when the data is stored in them. And the second is these technologies are emerging, meaning that they don't have, people who design them don't necessarily, at least at this point, have the extremely stringent mindset that people have locked into in existing technologies that have been around for more than 40 years, 50 years, right? Which means that it's a lot easier to get innovation, significant innovation into some technologies that are already emerging, because those technologies are already paying the cost of other things to emerge. and adding a little bit more cost may not be that bad into that, because that also increases the value. In the end, innovation is done to disrupt what's happening in the existing innovative field. If you can actually disrupt it in multiple ways, your opportunity to disrupt can be actually higher than otherwise. So there's an opportunity to integrate processing in memory to these technologies, not just only because they're more powerful with processing in memory, but also because the mindset is different. It's not just cost per bit, as we've discussed with DRAM, right? Okay. Basically, let's talk about the first one over here. So there's a very interesting opportunity over here, because existing systems that we have this sort of two-level storage model. Basically, you have memory that's separate from storage in today's system. Storage has traditionally been dominated by these hard disks, and it is non-volatile, it's slow traditionally, and it's block addressable. Basically, whenever you actually read something, you read an entire block, because the technology happened to be that way. It was more efficient to read an entire block, right, in a hard disk. Whereas if you look at memory, it's always evolved as not volatile, fast. Well, it's not always, but at least the dominant technology for more than 50 years has been DRAM, and it's volatile, and it's fast, and it's byte addressable. So you don't need to get a huge block, at least out of the DRAM chip. Internally, it's still somewhat block-based, like 8 kilobyte long rows, right? Those are blocks internally. But to be efficient, you can actually get out only 8 bytes, for example. It's byte addressable in the end. If you look at non-volatile memory, it combines some of these characteristics, maybe best of both worlds, right? Essentially, it's fast, it's byte addressable, and it's non-volatile. And it's somewhere in between these two memory and storage devices. So maybe it can enable the combination of memory and storage. So let's take another look at this. So basically today we have a true level storage model in the way we design our systems and in the way we program our systems also. And this two-level stores suggests that you have volatile data stored in main memory, and you access it directly through the programming interface, directly through the programming language. You do loads and stores, and you have a load store interface. And that is heavily accelerated in hardware. So you basically go through virtual memory, address translation, protection. All of that is done in hardware with some software support, of course. You need to inform the software also with the page tables and virtual memory system. Why? Because this device has been extremely fast. You cannot afford to have extreme. You basically don't want to slow it down with very slow software access. That's why this has been heavily accelerated in hardware. If you look at persistent data, it's stored in storage subsystem today, and it could be SSD or HDD, hard disk drives. And whenever you want to access it, you cannot do it through the programming language, at least in the dominant programming language of today. You have to go through system calls, operating system and file system calls to open the file, get permissions, read, write. They're all done through system calls, right? Now which means that there's a lot of overhead over here. Now, what existing systems do to get high performance is they memory map some of the files, right? But they need to go through the system calls to actually do the memory mapping, which means that they need to buffer the file into main memory. They need to maintain multiple copies, and that actually moves data around. But that doesn't get rid of the initial system call overhead and the final system call overhead, which may actually dominate depending on what are you doing to the file. If you're doing very small operations on a file, you may actually be dominated by this overhead over here, right? So basically, this two-level model becomes a bottleneck with non-volatile memory. If you replace storage with something like phase change memory with the characteristics that we discussed, that's very similar to this, now this operating system and file system calls become a bottleneck, because these are needed to locate, translate, and buffer the data, and these take on the order of microseconds, let's say, and this access latency of this is nanoseconds, like 50, 100, 200 nanoseconds. This doesn't make sense, basically, right? It's another way of putting what I said over here. Because you have this very fast device and you're wasting all of the performance that it can deliver. So maybe a better option is to reconsider how we actually design the systems today. And one reconsideration that may potentially make sense is looking at something like this. It's unifying memory and storage management with non-volatile memory. You have a unified interface and a single unit that manages it. Let's call it the persistent memory manager. We're going to add a lot of tasks to it, of course. It's going to eliminate the wasted work to locate, transfer, and translate data. We're going to use the load store interface to manipulate persistent data. And we may actually do more, as you can see. So this will hopefully improve both performance and energy because it doesn't have the huge software overhead. I'm going to show you some results with this. And hopefully this can simplify the programming model as well, because your programming model doesn't need to have this two-level storage model, right? You can basically achieve everything with loads and stores. Maybe you have special loads and stores to designate which data or what type of data you're dealing with, but you don't need to deal with files and file system overheads that you have. This is actually not necessarily a new idea. This interface can be actually underneath. You can have any hardware over here, right? And this interface can be load store based, and you can manipulate persistent data. And really old systems, actually, the Atlas computer, for example, one of the earliest systems, used to not have this two-level model between storage and memory. Everything was a single address space. There was no distinction between storage and memory. But later, devices evolved in different ways. DRAM was extremely fast, hard disks were extremely slow comparatively, and as a result, there was this dichotomy between persistent memory and volatile memory. And as a result, different interfaces evolved to take advantage of the device performance. But if the devices are now going back to something like this, maybe it's good to reconsider. Actually, there's a very beautiful book by IBM engineer Frank Soltis. He was the chief engineer of the IBM AS400 system. And he wrote this book called IBM AS400, Inside the AS400. We should put it up on the webpage. I don't have it in the slides over here. But this book, it actually starts, one of the earlier chapters starts with a case for making, this is called a single level store also. Basically a single interface for memory and storage. He basically says essentially what I said. We have this persistent storage system, we have this volatile storage system, and if we want to manipulate the data on the persistent storage system, we need to move a lot of data, go through a lot of software overhead, buffer a lot of data, and do an operation, and then put the data back into the persistent storage system. And then the question is, does it make sense? Can we just have a simple load store interface to do it? Now, they actually designed the system, AS400 system, to have single level stores. It was relatively slow because their persistent storage was not very fast, right? They didn't have phase change memory at the time. They used hard disks still at that time. But it's a very interesting book because they got rid of a lot of the software inefficiency, at least. They didn't get rid of the hardware slowness because they didn't have the technology to get rid of it, but they got rid of a lot of the software inefficiency. So I think that getting rid of the software inefficiency is extremely important if the hardware device is extremely fast. Otherwise, you may actually lose the benefit of the hardware device. So that's what we're going to try to do. So basically, this is it. We want to have persistent memory, and we want to manipulate it directly. So it provides an opportunity to manipulate persistent data directly. So what should this persistent memory manager do? To become more general, I think maybe you actually have loads and stores and internally manage the devices this way, because one of the fundamental principles that we discuss in this course is heterogeneity. And maybe your interface is load store, but internally, to get the highest efficiency, you have these different types of devices. And maybe the job of the persistent memory manager is to manage where the data should go and how do you respond to the loads and stores. And maybe you get hints from the software, operating system, and runtime to help with the data management over here. So it's a hardware-software cooperative system. It has to be hardware accelerated heavily, because today, if we want to access DRAM, it's very heavily hardware accelerated, right? The permissions, the access control mechanisms that we have in virtual memory, it's all accelerated in hardware. We cannot afford not to have hardware acceleration for non-volatile memory. Okay, so what should the programming model be? This is an example model over here where we actually can declare objects to be persistent. You can still use the file abstraction, but you don't manipulate files. In this case, essentially, you have you read your persistent data into an array, and that becomes a persistent object. And you can actually manipulate persistent objects. If your program is stopped in the middle, you start from the same location, and the manipulation that you've done to this array is persistent, meaning that you don't need to save or restore anything to a file. Right? And that's very powerful right now. Assuming that could be doable, you don't need to deal with this file system management at all, which is a lot of overhead. You can actually become more robust because let's say the system crashes somehow, and you don't lose data because you manipulated already your array in your persistent memory. of course, you need to ensure that you can restart the system at a consistent state, which we will also discuss later on. So it could be very powerful. So basically, this persistent memory manager uses access and hint information to allocate, locate, and migrate and access data in these heterogeneous array of devices. Let's go into it a little bit more. I'm not going to go into the detail, but this paper actually describes a bunch of tasks that are potentially useful for the persistent memory to do. It exposes a load store interface to access persistent data. Applications can directly access and manipulate persistent memory. There is no overhead in terms of conversion, translation, location. Of course, you need to design the hardware to ensure that there is no overhead. It manages data placement, location, persistence, and security. Of course, it's a mouthful. There's a lot. For example, there's a lot that these file systems do today in terms of security. How do you do that inside the persistent memory manager is important. But this is also a very open research area as well. How do you get the best of multiple forms of storage? It manages metadata storage and retrieval because you need to keep metadata about the data now. Because some data is persistent and it's really important to keep it persistent. Some data is not necessarily persistent. It's temporary data, for example. And you don't really need to keep it persistent. And if you distinguish between them, you can be much more efficient. But of course, metadata always leads to overheads that need to be managed, right? Let's assume that this huge part of your memory is persistent. This little part should be persistent, and this huge part should not be persistent necessarily. You need to somehow encode that in the metadata, right? This is very much similar to having virtual memory management for the entire storage space, which is a lot, while keeping the overheads in check. So that's the idea. How do you do that? Well, we don't know exactly how to do that yet, but we can evaluate the potential benefits. And hopefully it exposes hooks and interface for the system software and the application such that they can make better data placement and management decisions. So let's take a look at some examples. Basically, a persistent memory exposes a large persistent address space, but it may use different devices to satisfy this goal. For example, fast, low capacity volatile DRAM to slow, high capacity non-volatile HDD or flash, and other NVMe device in between. And of course, you can benefit from better data placement, as we discussed earlier. Let's take a look at locality and persistent. 2 dimensions. We discussed locality, but we didn't talk about persistent, right? So these actually are orthogonal characteristics. You may have data with less locality and more locality, and temporary and persistent. So for example, if you have a database columns in a column store that are scanned through only infrequently, right? You want to keep the database persistent, of course, but you don't have a lot of locality. Maybe this is a good example to place on the flash device, right? Or a storage device. You're streaming through. This is, again, as I said, streaming data. It needs to be persistent. It doesn't have a lot of locality. Maybe it's good for keeping in the flash or hard disk, where you have good streaming performance. Or if you have a frequently updated index for a content delivery network, this doesn't need to be persistent because you can always recreate the index as to what you should access. You can place it in DRAM because it's frequently updated and you have more locality. Of course, you can consider other characteristics like endurance as well, right, over here. Basically, you can provide hints for data placement using the persistent memory interface. That's one of the ideas of this. Let's take a look at the benefits of this with very system level evaluation. Right? For this evaluation, we're going to be very system level. We're going to look at several baselines. One is the hard disk level baseline. This is a traditional system with volatile DRAM memory and persistent hard disk. Basically, here you have overheads of operating system and file system code and buffering. You go through the file system. The second baseline is non-volatile memory. It's the same as this hard disk baseline, but essentially we replace the hard disk with non-volatile memory, phase change memory in this case, similar to the characteristics that we have for phase change memory. And we don't have DRAM actually. Non-volatile memory, in this case, we are assuming that there is no DRAM. So it's a bit crippled in terms of the system design. But even this is going to achieve a lot of benefits compared to hard disk baseline. Oh wait, sorry. This does have DRAM. Basically, you replace the hard disk with a non-volatile memory, and we still have the DRAM over here. Okay, keep that in mind. So basically here, the difference over here is you replace the hard disk with phase change memory. You can think of it that way. And you still have operating system and file system overheads of the 2-level storage model. Here, we're going to look at the persistent memory system, a more idealized system. Use only non-volatile memory and no DRAM to ensure full system persistence, or full memory persistence at least. All data is accessed using loads and stores in this case, which means that you don't have the file system and operating system overheads. You don't waste time on system calls, but there's some other overhead, which is this persistent memory manager overhead, which is examined in the paper Also, how long does it take to actually go through the persistent memory manager to do an access to memory? But data is manipulated directly on the MVM device in this case. But remember that this doesn't even have DRAM in the system, for we got rid of the volatile memory, so it's going to be crippled a little bit. So let's take a look at the benefits of this. This is for one application. Now I don't remember what that application was, but you can read the paper. Okay, it doesn't come to me. But basically the paper looks at a bunch of storage bottlenecked applications that spend a lot of time on storage access. And if you look over here, basically it's spending almost all of its time on system call I/O system calls. And this is the hard disk based system. Now, the performance of this is dominated by the device. Device meaning the storage device. The storage device is slow, so if you replace the storage device with a much faster device, phase change memory, you get a lot of performance improvement, 24x. This is purely based on the device improvement rate. That's a lot. Of course, maybe this is not the best baseline. We should have evaluated an SSD over here, which would have put us somewhere over here. So today's systems are probably over here with an SSD, right? At least high performance systems. Now the bottleneck shifts though. Here, if you look at this system, it's still the 2-level storage model. It has phase change memory and DRAM, and the bottleneck is now on the system calls. It's not on the device basically. It's not clear in this picture, but the device is less of a bottleneck, but really the operating system and file system calls are the bottleneck. Now if you actually change model persistent memory as I described with its overheads, but get rid of the system call overheads, you get significant performance improvement. It's about 5x. So basically this says that this system is not a good system design for a device like phase change memory, because you're wasting a lot of your overhead on the system calls. If you get rid of it and have a reasonable persistent memory based system load store interface, you gain 5x performance even though you remove DRAM from the system. So you remove the fast memory, your memory is overall slower, but you still gain a lot of performance because you get rid of the software overhead in the system. That sounds interesting, right? This shows that the software overhead is huge in the system. Okay, so that's the idea over here. There's a lot of research to be done, of course. And if you look at the energy benefits, they're actually similar. Replacing the hard disk with phase change memory buys you a lot of energy benefit. But again, if you have an SSD, it's somewhere over here probably. And getting rid of the system calls, replacing them with the hardware overhead of persistent memory management still buys you about 5x. Even though you get rid of DRAM and increase your access latencies overall to the device itself. So that's a huge potential over here. If you actually add DRAM into the system now, it becomes even more interesting. Maybe you can get even more over here. Maybe overall it'll be 10x or so. But the next works actually tackled that. Although I'm not sure if you're going to be able to get to the next works right now. Any questions? I've covered a lot of ideas over here actually. This is something that's still ongoing and there's a lot to be done in this area. But the potential is actually very large over here. Okay, so a huge challenge and opportunity is actually, especially with these new technologies, combining memory and storage. Now there are actually efforts in flash. Flash is actually interesting because people are trying to design very low latency flash today. I think Samsung has a ZNAND or something like that. But they actually have fast devices that they're trying to put out. Fundamentally, flash is not as fast as something like STT-MRAM, for example, but clearly those fast flash devices can close the gap between DRAM and existing flash devices. And even with flash devices, combining memory and storage is becoming, in my opinion, very, very interesting. Because there are a lot of benefits that you can get by getting rid of the software, huge software management layer that you have for storage today. So I believe this is going to change a lot into the future, and the software stacks that we have for storage is going to hopefully be much more leaner and much more efficient going into the future. Devices will drive a lot of that innovation. Okay, basically a unified interface to all data. Actually, I just talked about the unified interface to all data inside a single node, right? We're talking about a single node. What about multiple nodes? Actually, having unified interfaces is helpful in programming and efficiency as well. So if you're communicating between this node and some other node or some other place on the world, wouldn't it be nice actually if you had a single way of referencing everything? You do a load and that load automatically gets the data, I don't know, from a data center in China, let's say, and brings it to your computer. That's what this all data over here is mean. Of course, clearly we don't have that today, right? You can think of this as a huge glorified memory system that is actually able to access everything that's out there. We don't even have it in a single node today, right? Because we have clearly a 2-level model in a single node. But if you take this further, it's really everything out there is addressable with a single addressing mode. Single addressing mechanism, and you can access it with loads and stores. There could be benefits to that also. People are trying to do that in data centers, for example, especially with these fast non-volatile memory technologies, they want to have a single address space and single virtual memory management mechanism across the entire data center. Of course, there are a lot of challenges, but you could take it into a larger level as well. Okay, maybe I'll stop with this question. Basically, the next question is, how do you ensure consistency of the system and data if all of your memory is persistent? And this becomes a problem because if you actually have a persistent memory system, your system crashes, and you manipulated some persistent data, how do you ensure that whenever you restart the system, everything is consistent, meaning that you'll make, meaning that basically your program will run correctly after that. Right? If you haven't stopped things at a consistent place, you may actually have inconsistent data. For example, if something has stopped while you're manipulating a linked list, and some of the persistence is actually some of the links you formed and some of the links you have not formed, then you may have a problem, right? If you already updated the persistent memory. And of course, there are ways of handling this in software. You can have transactions that ensure that persistent memory doesn't get updated until you really know that you're in a consistent state, but those impose burden on the programmer. How do we actually do this without imposing a lot of burden on the programmer is the key question. And also, if your memory magically becomes persistent today, this becomes a problem in existing applications. Existing applications that are not transactional may not run correctly if your memory magically becomes persistent completely today. And enabling that transition path for existing applications is important also. So this is actually an important challenge, but we're not going to be able to cover that in the remaining 0 minutes that we have right now. Any burning questions? Okay, I'll see you tomorrow. Yeah, yes?
What's going to be in the exam?
Oh, we'll talk tomorrow maybe. But basically, I think it's going to study the homeworks, study the exam. Basically, everything that we've covered, okay, let's say until today, I'll exclude tomorrow, is fair game on the exam. Labs, homeworks, sample exams. But don't expect everything to be exactly the same, of course, so I'm not going to ask the same question, right? Yes?
To be sure, it's next Thursday during class.
It's next Thursday during class, yes, yes. November 8th.